So this is going to be joint work with Ken Bromberg and Koji Fujiwara. So all three of us were at MSRI 3 years ago when there was this semester in geometric group theory and Teichmuller theory. And we thought we should think about some problems kind of as a dare or a challenge, if you wish. And so we picked, the problem was to work on asymptotic dimension of mapping class groups. The goal is to show that mapping class groups have finite asymptotic dimension. And as I said, this was more of a joke, and in the end it kind of worked out. But what I think is most interesting about this project is that it led us to think about actions of groups on quasi-trees. So that's what I'd like to talk about. And to begin with, I'd like to give a little tutorial on asymptotic dimension. So I'll start with that. So first of all, the definition, which is due to Gromov, it's a notion of dimension that's kind of like a covering dimension, but the idea is that it should be quasi-symmetry invariant. Okay, so suppose you have a metric space, so X is a metric space, and then we'll say that asymptotic dimension of X is less than or equal to n, and so now you're supposed to, in your minds, recall the definition of covering dimension. And this is going to be very similar, except that the epsilon that appears in the covering dimension will become large, and it will be called R, maybe. So this means that for every R greater than 0, there exists a covering. Now, of course, in the usual dimension theory, the covering is by open sets, but here it's not going to matter. So let's say Ui of X. And there are two properties. The first property is that if you take any metric ball of radius r, centered at any point of the space, that ball intersects at most n plus 1 elements of this covering. So any ball centered at x with radius r, for x in x, intersects, is this too low? No. Intersects less than or equal to n plus 1 of the UIs. And the second condition is that the diameters of these sets have to be uniformly bounded. So the soup of the diameters of the UIs is finite. Okay, so it's a bounded covering, and these intersections, they're in the usual dimension theory, you would require that n plus 2-fold intersections are empty. Well, here the condition is that it's not only that n plus 2-fold intersections are empty, but in fact, given any R ball, and R could be large, that R ball sees only n plus 1, at most n plus 1 of these sets. Okay, so for example, if I look at the plane, if X is R2, then I'd like to show that the asymptotic dimension is less than or equal to 2. And so there is a picture that proves it, and it's the brick decomposition of the plane. So you divide the plane into strips like this, and then you tile each strip into squares, but you make a little shift so that all quadruple intersections are empty. And of course here I chose the scale so that R is like this. This is a typical R ball in the space. So no R ball is going to intersect 4 of the bricks. And incidentally, this is the same picture that shows that the usual dimension of R2 is less than or equal to 2, except that in that case the bricks are small. Okay, so what are some properties of asymptotic dimension? Well, there's the product theorem. Essentially, one takes a classical theorem about covering dimension and wants to prove the analog in this setting as well. And so the product theorem is that the asymptotic dimension of the product of two spaces is less than or equal than the sum. And so, for example, you can prove inductively that asymptotic dimension of Rn is less than or equal to n. In fact, it's equal to n. Another important property is that this is a QI invariant. So if you have two metric spaces that are quasi-isometric, then they have the same asymptotic dimension. In fact, even if they're coarsely equivalent, if there is a coarse equivalence between x and y, they have the same asymptotic dimension. And as a consequence, we can talk about asymptotic dimension of a finitely generated group. Right? So if gamma is a finitely generated group, then the asymptotic dimension of gamma is well defined. Okay. Now, somehow, a main tool in asymptotic dimension is due to Bell and Dronischnikov, and it's the analog of the classical Hurevich's theorem. So what is the Hurevich theorem in covering dimension? Well, if you have a map between, let's say, compact metric spaces, x and y, and let's suppose that every point inverse has dimension less than or equal to n, then the dimension of x of the source space is less than or equal to the dimension of y plus n. Okay, you have an inequality like this. And the asymptotic dimension analog takes the following form. So this is the Bell-Dronischnikov, Hurevich theorem. It goes like this. So we have a map f from x to y, and it's Lipschitz. It's a Lipschitz map between metric spaces. And now I have to make an assumption that corresponds to saying that point inverses have asymptotic dimension less than or equal to n. Well, here I have to do the following. I have to say so for every m greater than 0, you can look at the balls, metric balls of radius m in y, and you can look at the point inverses of these balls. So those are kind of thick fibers. And I want to know that these thick fibers have asymptotic dimension less than or equal to n. But moreover, I want to know this uniformly. So for every m greater than or equal to 0, the collection, so f inverse of the ball centered at the point y, radius m, so this collection as y runs over points in y, has asymptotic dimension less than or equal to n uniformly. Okay, and what I mean by this is that so given R, you come up with this covering where where the diameters of the UIs are bounded by some number. Well, I want that bound to be the same for all these spaces. Okay, so there are many spaces here. The coverings that I have for individual spaces should be bounded by the same. The diameters have to be bounded by the same number for all the spaces. Most of the time, this condition is automatically satisfied because these spaces these inverse images will turn out to be isometric to each other, or maybe there will be only finitely many isometry types. Okay, so what are some applications of this theorem? Well, so for example, if I have a short exact sequence of groups, finitely generated groups. Okay, so let's. Sorry, didn't write down the conclusion. Then this wouldn't be a very useful theorem without the conclusion. Okay, so then asymptotic dimension of x is less than or equal than asymptotic dimension of y plus n. Okay, so now an example is, suppose you have a short exact sequence of finitely generated groups. So A, B, and C are finitely generated. Then I can apply this theorem to the map from B to C, where I take the word metrics on all three groups. Of course, the word metric on A might not coincide with the metric inherited from B, but they're uniformly the same. They're coarsely the same. and you can easily check that the assumptions hold. So you see that the asymptotic dimension of B is less than or equal than asymptotic dimension of A plus asymptotic dimension of C. Okay. Now, what about you can try to set up some map from hyperbolic plane to something, say, one-dimensional, where you control the fibers and you try to apply this theorem. And of course, the first attempt might be to take the nearest point projection to a geodesic in hyperbolic plane. Well, that doesn't work because if you take an inverse image of an interval, which is a ball in the line here, then you'll get an object like this. And you don't really you'd like this preimage to have asymptotic dimension 1, and it's not going to have asymptotic dimension 1. But what does work is this map. So you're projecting along horocycles. Okay, so every point lies in a unique horocycle centered at this point, at the end point of this line, and then you send it to the intersection of the horocycle with the line. And that map satisfies the Beltrán-Nishnikov-Hurevich theorem and shows that asymptotic dimension of H2 is less than or equal to 2. And in fact, it's equal to 2. You can find an easy homological argument. There is a locally finite homology class. It's the fundamental class of hyperbolic plane. And if you had a covering by bounded sets with these intersections, say triple intersections empty, then you could map a hyperbolic plane to the nerve of that cover. And you could find the map back from the nerve by sort of approximate inverse. The composition is going to be bounded distance away from the identity, and that will be a contradiction because you cannot factor the fundamental class through something one-dimensional. Okay, and this generalizes to all symmetric spaces. If you take say a semi-simple or say a simple Lie group G, so you look at its K-n decomposition, and then the symmetric space X, which is G mod K, is of course AN, and it naturally maps to A. So that's just the analog of this picture here. You're mapping to A. The preimages are these copies of the nilpotent group, and so this shows that the asymptotic dimension of X is well, it's going to be less than or equal than the asymptotic dimension of A plus asymptotic dimension of N. Now, by the nilpotent group, you can use this trick to see that in fact asymptotic dimension is equal to its dimension. So you get, in fact, this is the dimension of X. So asymptotic dimension of X is the same as the dimension of X. Okay, because Teichmüller space is the analog of symmetric space. This argument, of course, shows that any lattice in a symmetric space is going to have finite asymptotic dimension because the dimension is bounded by the dimension of the symmetric space. So the analog of the symmetric space is Teichmüller space. There's even an analog of the K-n decomposition or I should say A-n decomposition. This is just the Fenchel-Nielsen coordinates for Teichmüller space. And if you know about those, then what you'll notice is that the trouble is that the point preimages are not isometric. Here, point preimages are all isometric to each other, and that's why this argument works. But in Teichmüller space, they're not. And in fact, we still don't know how to do it that way. That would be a pretty, I think, geometric Teichmüller theoretic argument that the Teichmüller space has finite asymptotic dimension. Okay, so I do want to conclude the tutorial with one more theorem, which is due to Gromov, and it's that this chalk spray. It's that if gamma is a hyperbolic group, then asymptotic dimension of gamma is finite. Okay, so let's think about how to prove this. I want to give you an idea. So we have this hyperbolic group, and I want to look at its Cayley graph. And here's the identity in the Cayley graph. And so you're going to give me, oh, maybe you'll recall, because I don't think anybody mentioned the definition. What this means is that if you take, in the Cayley graph, you take, say, 3 vertices, and you draw geodesics joining these vertices, then the resulting triangle is thin. There's some delta that doesn't depend on the choice of these 3 points, so that this triangle is delta thin in the sense that if you take any point on any one of these sides, then it's guaranteed that this point is within delta of one of the other 2 sides. So each side of the triangle is contained in the delta neighborhood of the union of the other 2. Okay, so we have this hyperbolic group, and we have a delta, and now you're going to give me an R, and I have to come up with some kind of a covering. And I may as well assume that R is big compared to delta. So I'll secretly assume that delta is very small. And then I want to draw metric balls of radius that's a multiple of 5R, for example. And also maybe I'll think of R as being an integer. So I have these balls. So here's these are the concentric balls. So maybe this is I don't know, 5R. This is 10R. I don't know. Maybe I'll just to save on the picture. So maybe this is n times 5R, n plus 1 times 5R, and n plus 2 times 5R. Okay. So and I can keep going like this. Okay, now for every vertex in this sphere of radius 5 times nr, so take one of these vertices on these spheres, I'm going to give you a brick. So the brick will consist of points in the kind of in the annulus region between the next 2 spheres. So it just consists of points whose distance to 1 is between n plus 1 times 5r and n plus 2 times 5r, with the property that there is a geodesic from that point to the identity that passes through this vertex v that we picked. Okay, so there's the box that's labeled with v. So this is u sub v. Okay, so the indexing is by the vertices on the spheres. So for every vertex in the sphere, you get a brick that sits in the next annulus and consists of points that can be joined to the identity by a geodesic that passes through v. Of course, geodesics are not unique, and you might have more than one geodesic, and in particular, these bricks might intersect. But they certainly cover the space, and what I have to convince you is that the multiplicity of the cover is small, in the sense that if I take a ball of radius r, that it's not going to intersect too many bricks. Okay, so let's suppose we have some w over here, and we have the corresponding brick. There's u sub w, and let's say we have a ball of radius r that intersects both of these bricks. Okay, so what does that mean? So I take maybe I'll draw this a little bit larger so that it includes this point, and I have another. So I pick 2 points in the 2 bricks that both sit inside this ball, and I join them to the identity passing through these 2 vertices, and I also join them to each other by a geodesic whose length, of course, is less than 2r, because the ball is of size r. So I get this triangle. Here's a triangle, geodesic triangle that I see, and I want to apply the thinness of the triangle. So for example, this vertex v has to be within delta of one of the sides. Well, this side is too far from v, so there is no chance. So it has to be close to a point on this side here. It has to be within delta of this point. Now notice that when you pick the point, now what is the distance to the identity? Well, it can change by at most delta. So in other words, that point is within delta of w. In other words, the conclusion here is that the distance between v and w is less than 2 delta. So if you have a picture like this, if this ball of radius r intersects both of these bricks, then the the points that define the bricks are within 2 delta of each other. And so if you think about this, that says that the multiplicity of the cover is bounded by the number of points in the ball of radius 2 delta. And that's independent of r. So you conclude, this argument shows that the asymptotic dimension of gamma is less than or equal than maybe, I have to say 2 times the number of points, because I could draw my ball so that it intersects 2 annuli. So I have to multiply by 2. 2 times the number of points in the ball of radius 2 delta. Okay. So that's of course a finite number. So one problem with this argument is that it only shows finiteness. It doesn't show. It doesn't give you a reasonable bound. This number is probably pretty big, even if the asymptotic dimension is small. If you, for instance, for surface groups, you can try this for surface groups, and your bound is going to be much more than 2, which is the right answer. On the other hand, for trees, this works out. Okay. I'm not sure about. Maybe this number is not exactly right. But for trees, delta is equal to 0, and in that case, you actually get that the asymptotic dimension of a tree is 1, or maybe 0 if it's bounded. Okay. So now let's switch to mapping class groups. Okay, so again to recall the definition. So we have a compact surface, closed oriented surface, and I take so MCG of sigma. This is just going to be the group of diffeomorphisms, orientation preserving, divided by the component of the identity. And our theorem is that asymptotic dimension is finite. So I should say that the reason people care about finiteness of asymptotic dimension, even if they don't know the exact answer, is that it then implies Novikov type conjectures for the group. So we still don't know what the right answer should be. The conjecture is of course that it should be equal to the virtual cohomological dimension of the mapping class group. But the proof doesn't even come close to that. In fact, the reason that we don't have a good bound is in the theorem of this is maybe the first step of the proof. This is the theorem of Bell and Fujiwara, which says that the curve complex associated to sigma is finite asymptotic dimension. Okay, so C of sigma, this is the curve complex of sigma, and I'll remind you what it is in a minute. Then asymptotic dimension C of sigma is finite. Okay, so what is the curve complex? It is a simplicial complex. So let's say in genus 2. Let's keep picking. The vertices of this complex are going to be, say, if you want to think geodesic, so you fix a hyperbolic structure on the surface, and you think about geodesics, or if you don't want to do this, you just think about essential simple closed curves up to isotopy. So the vertices are essential simple closed curves up to isotopy. So here's another one, and maybe here's another one. So this is alpha, beta, gamma. And then if I have a collection, finite collection of simple closed curves that can be realized up to isotopy by pairwise disjoint curves, then I put a simplex there. So simplex is a collection of pairwise disjoint. Simple closed curves. And so in this picture, for instance, alpha and gamma would be joined by an edge, and so would beta and gamma, but alpha and beta would not. Okay, so this is a subcomplex of the curve complex. And an important theorem is due to Mazur and Minsky. In fact, we'll be using a lot of facts from the Mazur-Minsky theory. It is that the curve complex is hyperbolic. So C of sigma is hyperbolic. However, it is not locally finite. So this Gromov argument doesn't work. That is, the argument works, it's just that this number here is infinite, so you wouldn't be able to conclude anything. But Bell and Fujiwara came up with a trick to make it work, and it turns out there's a notion of tight geodesics in a curve complex, also due to Mazur and Minsky. And these tight geodesics are better than geodesics. And they satisfy some finiteness properties that, that replace the fact that the curve complex is locally infinite. So that, in fact, the argument just works. So you only, in the definition of these bricks, you have to, the only thing you do is insert the word tight. So you define the bricks by saying that this is the set of points that admit a tight geodesic to some base point. And then it turns out that everything works. Okay, so that's kind of the starting point. Now, of course, what's tempting is to say, well, look, we have an action of the mapping class group on the curve complex. And so therefore we have an orbit map. So there's a map from the mapping class group to the curve complex, which is Lipschitz. So let's just apply the Hurewicz theorem. But unfortunately, that doesn't work. It is tempting because individual fibers are smaller mapping class group. The stabilizer of a curve is basically a smaller mapping class group. But if you look at the ball of radius 1, it turns out you can't really say much about the preimage of a ball of radius 1. Okay, so let me give a little outline of how this goes, and then I'll try to explain the steps. Okay, so outline, and this will take us to group actions and quasitrees. Okay, so step 1. So we'll come up with an action of the mapping class group on a finite product of hyperbolic spaces. So construct, and this will have very much to do with quasitrees. Construct an action of the mapping class group on a product. So it's x1 cross x2 cross xk. It's a finite product. So that the orbit map is a quasi-asymmetric embedding. So you have MCG into the product is a QY embedding. Okay. And then step 2. We'll show that each of these xi's is hyperbolic. And not only that, it comes with a natural map to something called Ti. So each xi is hyperbolic and has a map xi to Ti that satisfies, can you see this? It's okay. That satisfies the Hurewicz theorem. Okay, and not only that, but the preimages of the fibers associated to this are curve complexes of subsurfaces. So the fibers and the fibers of xi to Ti are C of, I don't know, sigma primes, where sigma prime is the subsurface of sigma. Okay? So the point is those have finite asymptotic dimension by the theorem of Bell and Fujiwara. So we're kind of in good shape. In other words, after steps 1 and 2, we're reduced to showing that each TI has finite asymptotic dimension. So we're reduced to showing asymptotic dimension TI. Because then by these theorems, it will follow that Xi also has finite asymptotic dimension. And then by the product theorem, this product has finite asymptotic dimension. And then, of course, the mapping class group, which sits inside, quasi-asymmetrical embedded, also has finite asymptotic dimension. Okay, so this is where we were not long after we started the project. But we were stuck on this. We didn't know what to do with TI. TI is something very explicit that I will try to describe. But then we realized that what's going on is that the TI is quasi-asymmetric to a tree. And that's one way to show that a space has finite asymptotic dimension. Show it. It's a quasi-tree. Okay, so that's step 3. TI is a quasi-tree. A quasi-tree is you can think of it as a graph, which is quasi-asymmetric to a tree. Think of taking a tree, thickening it, and then taking the one skeleton of the thickening. That's a typical tree, a quasi-tree. Okay, so asymptotic dimension of TI is less than or equal to 1, and so we're done. So this is QED. Okay. Okay, and this really is the maybe most interesting part of this program is how you construct these TIs. And then it turns out that everything is axiomatic. You just need some fairly simple axioms, and your construction will give you a quasi-tree. So that's the next thing to explain. Okay, so axioms. Okay, so Y is going to be a set. This sort of fancy Y. This is just going to be a set. And of course, in the background, maybe there is a group that's acting on the set, so that the quasi-tree we produce will be acted on by that group. Okay, so this construction will be equivariant if there is a group acting. And for every, for say A, B, and C in Y, we have a number. A number that's it's called the projection distance. So this is something like the distance between B and C is seen from A. Okay, so and these are supposed to be distinct. Okay, and then the axioms are, so this is some real number greater than or equal to 0, and then the axioms are it's symmetric. The distance measured from A between B and C is equal to the distance between C and B. There is a triangle inequality. B and D is less than or equal to the distance in A between B and C, and plus the distance from C to D. And then there is this inequality that's sometimes called the Baerstuck inequality. So there exists some constant, universal constant, with the property that of the three numbers, so you have the distance measured in A between B and C, and then you also have the distance measured in B between A and C, and the distance in C between A and B. Two of these numbers have to be less than or equal to C. At most, one is bigger than C. Yeah. I'll give you an example. Yeah. At most, one is greater than C. And then finally, so there's some other number k0, say, so that the set of so that for every a and b, the set of c's, so that the distance measured in c between a and b is greater than k0 is finite. There are only finitely many big projections. This is, of course, motivated by the hierarchies. Okay, so here's an example. And this is somehow where negative curvature will come in. Okay, so example. So let's say we have a group acting discretely on hyperbolic plane, say, or hyperbolic n space. So gamma acts on H2 discretely. And we have, and maybe gamma, little gamma is the axis of some element of gamma. Okay, so here's hyperbolic plane, and here's this gamma. And then now I want to take the orbit of this axis by the group. So I'll get a bunch of other lines. Of course, they might intersect, but I don't want to crowd the picture. Okay, so that's roughly the picture you see. And I want to take y to be this orbit. So this set y is going to be the orbit of gamma. And then I take the distance. So if I take 3 of these, so let's say this is A, there's B, there's C. So what is this? Well, I project B and C to A. Okay, so take the nearest point projection. So B projects to A, it projects to some interval in A. And C projects to some interval in A. And these are finite intervals. And then I take the diameter of the union. So this is the diameter of the projection of B to A, union projection of C to A. Okay, so that's the distance between B and C as seen from A. Okay, and the most interesting axiom to verify is this inequality. That if you take 3 of these, then you can't have. It couldn't be that 2 of these are big. At most 1 can be big. And that's you should kind of try to convince yourself that this is correct. But basically, if you have, so let's say this is A, and here's B, and here's C. So this is an example where the distance measured in A is big between the projections of B and C. But then you take there's a geodesic connecting A and C, and it's very far from B, and you project that over here, and this is going to be very small. That will show that the distance in B is small. Okay. The distance between B and B? Well, that's not allowed. They're supposed to be different. It's not, it's not 0 for, and also it can, this is all somehow coarse. Small numbers are as good as 0. Okay. Okay, so now, maybe I should give some more examples before we continue. Maybe. Union, just a union. Okay, you have projection of one axis to another is some kind of a small set. And the other one is also a small set. Will it take the union? They could be far apart. That's what this distance is measuring. What? You could take what? Oh, the span. Well, okay. In this case, it doesn't matter. Yeah. Okay. Okay, so here's another example. It's really kind of the same thing, but gamma could be any hyperbolic group. And then, of course, these axes are not quite well defined. You have to talk about quasi-axes and or equivalence classes of axes or whatever, but you can basically the same thing generalizes. You can take an axis of an element and look at the orbit and look at the projections. Now this also generalizes to groups like mapping class groups and out-FN. Well, it's maybe out-FN. So there's a work of Yael Algom-Kfir. So she showed that, so there are these elements in out-FN called fully reducible, as Martin was explaining the other day. And she showed that that they have good projection properties, so that these axioms hold. Okay, but for us, the main example is that of subsurface projections. Okay, so now sigma is going to be a surface as before, and for the set Y, we're going to take all essential subsurfaces. So this is the set of essential subsurfaces. It's an infinite collection of sigma that includes sigma as well. Sigma is also considered to be a subsurface of itself. Okay, so now if you have I should also I should make a So instead of saying all essential subsurfaces, let's think about a subcollection. This is a set of some essential subsurfaces of sigma, and the property that I want is that if you take two of them, then their boundaries intersect. So if I take say a subsurface, which could be an annulus. So here's an annulus subsurface, and then here's maybe another one, which is also an annulus. I want their boundaries to intersect. Okay. So if A and B are in Y, then I want to know that boundary of A intersect boundary of B is empty. Is not empty. These are these subsurfaces are realized in an efficient way. So it's you're not allowed to draw two subsurfaces that are disjoint and then draw them inefficiently so that they intersect. Okay, so this intersection is essential. These are the subsurfaces are defined up to isotopy anyway. So you cannot isotope A and B in such a way that their boundaries become disjoint. Okay, that's the condition. And then if I have this collection Y, then I can define the subsurface projections. So so what is the distance? So I have three of them now, and I want to define the distance between B and C measured in A. So what I do is I restrict the boundary of B and C to A. So I take the boundary of B and restrict it to A. So what is that? Well, maybe this is A and this is B. So when I do this, I'm just going to get some collection of arcs in A. And I do the same thing with the other one. Boundary C restricted to A. So I have two collections of arcs. And these arcs are going to, of course, be pairwise disjoint within each collection. So I could just pick one of the arcs in the collection. And then I want to measure the distance in the curve complex of A. Okay. Now the curve complex of A, I only talked about curve complexes for closed surfaces. When you have a surface with boundary, then you also allow arcs. That's maybe the easiest way to think about the curve complex of A. So these essential arcs are also vertices in the curve complex of A. And so you have two arcs. There's an arc from here and an arc from here. You can measure the distance in the curve complex of A. So you get some number, and that's the definition. And Maser and Minsky and also Berstog in his thesis checked that these axioms hold. So this is somehow our setup. Okay. And now let me state the theorem that how do you get a quasi-tree from these axioms? Okay, so let's go maybe over here. I won't need the axioms really. Okay, so we define the projection complex. So the projection complex. So this is going to be a simplicial complex, and the vertices are, or even the graph, vertices are just the elements of this set Y. Okay, so for example, the axes here, each axis is going to be a vertex. And then I'm going to put an edge if there are no big projections. So we, maybe to begin with, we fix some very large constant. So fix some k that's much bigger than the constant you had before, k0 and xc. And the projection complex has the vertices, maybe we'll call it p sub k of y. So vertices are elements of y, and you draw an edge between two of these if there are no big projections. In other words, if yeah. No, that's going to be, this projection complex is going to be a TI. Okay, so we do this if for every c, the distance measured in c between a and b is less than k0, less than k. So all projections are small. Okay, if all projections are small, then you draw an edge between the two. And I'm cheating a little bit. It turns out that we have to perturb this distance slightly to make this work. If you think about proving, say, that this complex is connected, then you'll quickly see a need for perturbing the distance. But I'll skip this point. Okay, so then the theorem modulo the slight lie is that the pk of y is a quasi-tree. Okay, so you have a way of constructing lots of quasi-trees. So, for example, any hyperbolic group is going to act on a quasi-tree in some interesting way. Notice that that's very different from trees. I mean, somehow the slogan in geometric group theory is that you can always remove quasi. If you have an action on a quasi-tree, then you should have an action on a tree. Well, that fails. For example, for hyperbolic groups that happen to have property T. Those groups don't act on trees in any interesting way. They always have to have a fixed point. But any hyperbolic group is going to have lots of actions on quasi-trees from this construction. Okay. So maybe let's go back to those to the outline. So maybe, let's see, 15 minutes. Here's an example. This is kind of a warm-up for how this is going to work. So I want to take maybe a genus 2 surface, and I'm going to take this annulus here, the one that separates the genus 2 surface into two tori, and I'll take the orbit of this annulus under the whole mapping class group. In other words, I'll get all annuli that separate the surface. Okay, so take Y to be the set of all annuli in sigma 2, genus 2 surface that separate the surface. And so the point is that any two will intersect. You cannot draw another annulus disjointly from this one, and so it still separates. So that collection will satisfy our axioms. Any two surfaces in our collection intersect. So we have the mapping class group acting on this collection, and so we get an action of the mapping class group on the quasi-tree. Right? So T, if T is this projection complex, pk of y, then this is a quasi-tree, and the mapping class group is acting on this. It's a quasi-tree. Okay, now that's not quite the quasi-tree I like. There's a better one, and it's a blow up of this tree, and that's going to be the x, the corresponding xi. Okay, so now construct x. Okay, so what is x? So each vertex of this T represents, of course, one of these annuli. Or secretly, it represents really a curve complex of the annulus. The curve complex of the annulus is really a line, or something quasi-isometric to a line. Because if you think about, so there are arcs that you're supposed to be looking at the arcs, essential arcs in the annulus. So a typical arc is just going to start from one boundary component, it's going to wind around n times, and then it'll end at the other boundary component. So this n really is what matters. So the curve complex of the annulus is quasi-isometric to z or to r. Okay, so we blow up each vertex of T to the curve complex of the annulus it represents. Okay, so given say one of these edges in T, so here is the picture of T. It's some kind of a quasi-tree, but I may be thinking of it as a tree. And now each vertex here gets replaced by basically a line, something quasi-isometric to a line. Now what do I do with the edge? So I need some collection of edges joining the two lines. And what I do is I look at the projection of one of the annuli to the other. So they'll have two annuli and they'll intersect. The intersection is a collection of arcs. But these arcs are all adjacent because they're disjoint. They're all adjacent in the curve complex of A. So you get some kind of a small set here, and you get a small set here, and you draw all possible edges joining the points in these sets. Okay, so that's an equivariant way of lifting this bridge up to a collection of bridges. Okay, so this just happens everywhere. So you have another line corresponding to this vertex here, and you have some bridges, and so on. Now, it's a theorem that's just a little a fancier version of this, namely that this x is also a quasi-tree. Okay. But notice that the Dane twist, take a Dane twist, say, supported on this annulus A. Well, what is that going to do? Well, that Dane twist will act hyperbolically on the corresponding line. Right, it'll shift, an arc that winds around n times will wind around n plus 1 times after you apply the twist. So it's acting kind of like a translation on this, on the curve complex of A. And so we have an action of the mapping class group on a quasi-tree, so that a Dane twist acts hyperbolically. And Martin was saying the other day that this can't happen in the cat-zero world. So, for example, an application is that there's no cat-zero equivariant thickening of this quasi-tree. There's a quasi-tree, but you cannot thicken it. For example, you cannot replace it by the Rips complex with some large, D in the PD of the definition of Rips complex. So that the Rips complex becomes cat-zero. Okay, so the way that this works for the mapping class group is that you divide. So here's a fact that the curve complex of the surface is finitely colorable. That is, you can color each curve on the surface using finitely many colors, so that disjoint curves get different colors. Okay, so there's a finite chromatic number, if you want. So that's a fact. So the curve complex of the surface is finite, has a finite coloring. Okay, so in other words, what that means, adjacent vertices get different colors. And that's, and again, a slight generalization of this says that you can divide the collection of all subsurfaces we just kind of have to make this example slightly fancier. So divide the collection of all subsurfaces of sigma into into finitely many classes. So say y1 union yk, so that within each class. So it turns out you can make it invariant under a finite mixed subgroup of the mapping class group. Okay, so there's a finite coloring. In fact, it's invariant under not the whole mapping class group, but that's clear because you can take a curve to a curve this disjoint. But it's invariant under finite mixed subgroup. Okay. So we can divide basically by looking at the colors of the boundary. And that's not very hard. So you can divide the collection of all subsurfaces of sigma into finitely many classes, so that within each class our axioms hold. So any two they have intersecting boundaries. So that if A and B are in yi, then the boundary of A intersect boundary of B. It's not empty. Okay, and so that gives us so this yi is going to give us ti, and then the blow-up construction will give us xi, and we have this xi maps to ti by construction, and the mapping class group acts on the product x1 cross xk. Okay, again by construction, mapping class group acts on the collection of subsurfaces, and the fact that the orbit map is a quasi-asymmetric embedding is a consequence of an estimate of Mazur and Minsky. So Mazur and Minsky estimate. They imply that this orbit map from the mapping class group into this product is product of the xi's is a quasi-asymmetric embedding, and that really completes the proof because that was the step one. If you remember the steps, so we said we would construct a finite collection of spaces and an action so that the orbit map is a quasi-asymmetric embedding. And so the Ti is a quasi-tree, and the Xi has finite asymptotic dimension by the Hurewicz theorem, and therefore the mapping class group also does. This was really, we knew this first step ahead of time. We just didn't know how to show that these Ti's that showed up had finite asymptotic dimension. But we knew about the Mazur-Minsky formula, and if you know about their formula, then it sort of involves, it's an infinite sum. And so we try to organize this infinite sum into a finite sum, and that's somehow what the finite sum by combining the terms that correspond to individual yi's, and that's somehow where this came from. Okay, so maybe I better stop here. Thank you. Well, for the Pence complex, you want to take surfaces that don't contain annuli. You throw away the annuli, and then you get something. The Pence, you get the Pence complex embedded in just like here, except you get the Pence complex embedded if you omit the annuli that appear here. Then that's right. Yeah, so you can show that also has finite asymptotic dimension. No, nothing here is locally finite.